Um, okay, so I guess we'll get started. So try to give a few minutes because I know that you have to trudge in unfavorable conditions early in the morning. But sorry about that. I don't choose the time for the class. But welcome to 6045. This is Automata, Computability, and Complexity. That's the formal name for the course. Its nickname is Great Ideas in Theoretical Computer Science. I'm Scott Aronson. This is my seventh time teaching it since I've been here, so I'm starting to get some idea of how to teach it, although I'm still learning. We have 3 TAs. So we've got Adam Yedidia, who's there. Hi, Adam. We've got Saeed Maraban, who's there. And we've got Kevin Wu, who I think who emailed that he hasn't made it in yet because the delays on the red line caused by the snow. But when he gets in, we will point him out to you. Okay, so this is the Stellar site for the course there, and we do have a syllabus online. I didn't print out paper copies because that just seemed too old-fashioned. I don't know. And I will go through the syllabus in class a little today before we get started. We have what looks like a record enrollment this year for 6045. That could be because of this huge surge of intellectual curiosity about computability theory. Maybe it's that everyone saw the movie The Imitation Game. I don't know. Raise your hand if you saw it. Okay, a fair fraction. All right. Well, it has it has something to do with Alan Turing. The movie, took a lot of liberties, but we'll learn some of the reality of what Alan Turing did in this class, along with Gödel, with Shannon, with a lot of really great stuff. But anyway, it could also be just that all the Course 6 enrollments have been surging, and it could be that for the first time since I've been here, this course now counts as a header, so you can take it or 6046, right, for a header in 6.3, or what I'd recommend, you can do both. Okay, but all right, so let's see. Let's go through a few things. We do have a Piazza site for this course. There's a link to it from the Stellar site. Piazza is just like a Q&A system. So I've used it. I think the past 3 times that I've taught this course, students have really liked it. Anything that's unclear to you in lecture, any clarification questions about the homework, not like, do problem 3 for me, but like, I don't understand what the question is asking, or, things like that. So you can ask, and then, the questions could be answered either by the TAs, by me, by other students. And then if you have student answer questions, like we can endorse them as being good answers, or we can add our own comments. It's a really good resource. Okay, so I encourage you to use it. Of course. you should interrupt. And I mean, the class is not, even though this is kind of a little bit of a forbidding lecture hall, you should just please interrupt anytime you have questions. I mean, look, I mean, you're all coming here at 9:30 in the morning, right? I would like to provide you some sort of value added for actually, physically being here, right? I mean, if it was just me standing and talking, right, then you could just, watch a YouTube video, or you could just stay home and read the textbook. Okay, so let's try to, provide some value added. I mean, I love to interact with the class. The one danger is that, if you say, if you raise something interesting, I can very easily get sidetracked, right? I can very easily just, spend 10 minutes of, on just, like, oh, that's an interesting direction. I'm glad you asked. So just beware of that. And what else? Oh yeah, so books. So this is the main textbook for the course. It's Intro to Theory of Computation by Michael Sipser, who's now the Dean of Science here, I guess. It's not sort of my style to follow any one book too closely. So like I'll assign my own problems. I mean, you could even get through this course without using the book at all. But I recommend it. Okay. So Sipser's book will roughly cover what we do for like the first 60% of this course or so. Okay, and so it doesn't cover the stuff that we'll do toward the end of the course, but it basically it covers like the the basics of theoretical computer science. Okay, but the basics that it does cover, it does a really good job. It has a lot of intuitive explanation. Like like for each one thing that I love and that I wish would become standard is that like every time he proves a theorem, he says like first here's the idea of the proof, and now here's the gory details of the proof, right? And he just has but he always just states the idea first, and let's see. I mean, then the stuff that we'll do in the rest of the course. There are several books. This is a book I wrote. It's called Quantum Computing Since Democritus. I don't want to sort of advertise it or push it too hard on people. But if it does cover some of the stuff we'll do at the end of the course. There are other books that do that. There's one by Moore and Mertens that I really like. There's one by Aurora and Barak. Okay, these are all strictly optional. In addition to books, we're also very lucky to have lecture notes. We've got, from the first time I taught this course at MIT in 2008, we have scribe notes, and those are all just available on the Stellar site. And they're not perfect. They have they've got some mistakes in them. 'Cause they're scribe notes. That's what they are. But and they and we're not going to be perfectly following them, but we'll be more or less closely following those. So those are also a resource. Okay, so in terms of grading and what's expected of you. So there are going to be 6 p-sets in this course. You'll generally have about 2 weeks to do each p-set. So we haven't yet set the due dates for all the p-sets, but we'll do that this week, and we'll put that up on the Stellar site. So you're welcome to collaborate, form study groups, work on the problems together. But we just ask that sort of the usual rules that you write up your solutions yourself, and that also you list the names of anyone who you collaborated with. Okay, so unfortunately we do require you to turn in the PSET sort of physically, not just by spirit or by telepathy, and not online either, because we've done sort of online submission in the past, and it's kind of been a mess for in terms of grading. I have like PSET boxes outside my office where you can turn them in. You can also turn them in during recitation, which I'll get to, or in class. Okay, all of that's fine. Let's see. Okay, so there will be two. There will be one midterm and one final. And we haven't yet set the date for the midterm. And by the way, if any of you have dates where you know that you'll definitely be away or definitely cannot make the midterm, now is the time to tell me, send me an email, and I can try to accommodate requests if I get them now. Okay, so we'll set a date for the midterm, and then the final. I don't even control the date for that. That's just during finals week. Okay, and that's the midterm will be in class. Okay, and so the midterm is, I think, like 25% of your grade. Finals 35%. The PSETs are 40%. And then we also have like a small participation component. So if you're someone who's been participating in class a lot, coming to recitation, participating in recitation, asking questions, participating on the Piazza site, coming to office hours, that's all stuff that can if you're like right on the boundary between an A and a B or something, that can make a difference. Okay, so let's see. Okay, office hours, I should say. Okay, so my office hours are Tuesdays 11 to 12, so basically just right after lecture. Okay, or if you can't make that, then you're always welcome to email me and make an appointment. And we're going to figure out office hours for the TAs to try to maximize the chance that everyone will be able to make at least some office hours. Okay. Say my office is 32. Is that? But you can also just like come to me after class, and we'll walk back together to the office if you want to go to office hours. Okay. So what else? Yeah. Okay. So recitations. Recitations are on Fridays. We have like 6 slots that are available to us for doing recitations. We're not going to use all of them. We only have 3 TAs, and I think we'll do 3 recitations, and so we still have to choose slots for them. I think we have like 10, 11, 12, 1, 2, and 3. So we'll try to choose slots to maximize the number of people who can make a recitation, which hopefully all of you will be able to, and then you'll choose a recitation that you'll go to, and if you want to switch once in a while, that's fine, but you should sort of have a main recitation that you're going to on Fridays. Okay, and the recitations are actually important because my lecturing style, I tend to be a big ideas person. I love talking about, the history, where things come from, what they mean, in terms of working out examples. This is something that where I know that, I'm not the best in the world. I try, I really do. Okay, but in terms of, like I might do one example of something, right? But then, you want to see more examples, right? You want to see, how to solve problems like the ones that you're getting on the, on the PSAT. Then, recitation is really useful for that. Okay, so any questions about the administrative stuff? Anyone? Okay, so if not, then we can get started. So okay, so what's the point of 6045, right? Well, why are you taking this course? There are lots and lots of Core 6, courses where you learn something that will be, useful to you in the real world, in industry. This isn't one of them. You might learn something useful in this course, okay? But if you do, it will be sort of accidental, okay? This is the course where we try to show you why, computer science sort of deserves the name science, right? Where we, try to show you the intellectual depth of the field, its historical roots, its the speculative places where it could go in the future, and this is a course where we try to blow your minds by showing you what's possible, in terms of undecidable problems, Gödel's theorem, cryptography, the P versus NP question, quantum computing, things like that. Okay, so and look, it's when in the future, you hear, news about, exciting new developments in cryptography or in, physics and computation or whatever, right? This course will sort of give you an intellectual context for it. I mean, the good news about this course is that what we teach here, is not going to go out of date anytime soon. Okay, so there's a quote that I really like from Edgar Dijkstra, who was, the inventor of Dijkstra's algorithm, famous computer scientist, and he said, computer science, is no more about computers than astronomy is about telescopes. Okay, so what did he mean by that? He meant that computer science is a sort of set of tools, often, mathematical tools. This course will concentrate on sort of the mathematical side of things, but, there are other sides as well, right? It's a body of ideas, by which you can try to, understand anything, really, right? Any kind of rule-governed system whatsoever, whether it's a cell or a brain or, a set of physical laws or an economic market or, yes, a computer, okay? And I sort of got into computer science, as a kid because I wanted to understand how video games worked, right? And, it seemed clear, right? Really I'd like to understand the physical universe, right? But it's very hard to ask the creator of the physical universe, why did they make the design decisions that they did, right? Why did they choose, for there to be 3 spatial dimensions rather than, 2 or 17, right? But but video games, I mean, someone created them, right? So someone must must know the answers to these questions, and and sort of you could have imagined a priori, right, that creating a video game, would have been kind of like building an airplane, right? It would have been this big, engineering problem, right? You would have a factory, like for maybe like for each level of the video game, there would be like a different part of the factory where that level was assembled. But no, it's actually it's really just these lines of code, right? It's like which are in some sense just expressing mathematics. And they're not just some kind of summary of the game. They are the game, right? You change them, and the game does something different. When it's very, very easy to take these sorts of things for granted because they're very obvious to us now, right? When I first saw it, it was like learning where babies come from or something, right? It was a revelation. So one thing that we try to do is to sort of reawaken just sort of how surprising some of these ideas were. When someone had to discover in the first place the idea of computational universality, right? And sort of taking you through the thought process that that led people like Turing to these ideas. Okay, so let's see. So the field that is normally sort of seen as trying to understand how the how the universe behaves, how it's put together, is physics. But you could think of physics as sort of working in the opposite direction from computer science. With physics, you start from the phenomena, and then you sort of work downwards, right? You find better and better theories that that explain more and more, that are more and more explanatory, and then you hope that eventually you'll have this grand unified theory that will basically just be the code of the universe, that you just execute it and you get us, right? So computer science in some sense I think of as working in the opposite direction, that you start from a set of rules which don't they could be inspired by physics, but they don't have to be. They just have to be some kind of well-specified rules, and then you work upwards. You say, what can we build by using these rules, right? By composing these rules together, what kind of behavior can we get, and what kind of behavior can we not get? Can we, understand it mathematically? Okay. So just to sort of whet your appetite a little bit with where we're going in the course. So there's one little a vignette that I like to use in the first lecture, just to sort of give you an idea of the sorts of things that we'll talk about. And this is the problem of how do you set up an online gambling site. Okay, so let's we'll assume that you've sort of gotten past all the the legal issues. You've set up your server in the Cayman Islands or whatever. Okay, and you want to run an online gambling site. Okay, so for simplicity, let's say that you want to have an online roulette game. Okay, so people can bet on either red or black, that a wheel will land on, and if they get it right, then they win $1, and if they get it wrong, then they lose $1, plus some commission for the house, obviously. Okay, so so you set up this site, you start running it, okay, and then there's sort of an obvious difficulty, right? Which is that the way the internet works is, messages get sent one at a time, right? Someone has to speak first, right? So the gambler could say, well, I bet on red, okay? And then, the website could send a message back which says, sorry, it was black, okay? And then, the gambler could say, well, I bet on black, and then the house says, well, sorry, it was red, okay? And then they say, well, all right, I bet on black again. You say, well, sorry, it was red again, okay? And you say, I bet, all right, fine, I bet red. And they say, sorry, it was black, okay? And if this goes on enough times, you might begin to suspect for yourself that that something is wrong. You might stop using the site, okay? I mean, this is problem, real casinos have also. You have to pay out sometimes, or people will just stop playing. Okay, but let's say that you just had a really big, you just had a one-time gamble for really high stakes, right? Someone's going to bet, $1 million on red or something. Okay, then we would like such a discriminating customer would really like to have some kind of guarantee that that the software isn't cheating, right? That the software actually picked whether the wheel was going to land red or black before the before the gambler came in, right? So then the question is, how do you do that, right? I mean, in the in a physical casino, you just set the ball in motion, and then people place bets while the ball is still rolling, right? But that's not going to work online. Okay, so what else could you do? Well, you could have the house just say, well, okay, the ball landed on black. What do you bet? And then the customer says, "Oh, what a coincidence! I happen to bet black." Right. So all right. So clearly that's not going to work either. Okay. So can anyone suggest another solution to this? Yeah. Yeah. So basically, what you want is some sort of way of committing yourself, right? So physically, like if we were doing this over paper mail, you could just take your bet, put it in a sealed envelope, or put it in a safe or something, right? And then so you haven't revealed it to the casino, but you have sort of committed to the casino that here is a place where I have committed my decision and I'm not able to change it, okay? And I can reveal it to you later. Okay? These are all properties that are important, right? And then the casino could say the ball landed on black, and then you can open up the safe and show what you bet. Okay, so then the question is, how do you do that over the internet where you don't have physical safes? Okay, and the modern solution to this sort of problem is to do it by assuming that certain problems are intractably hard, right? Not literally impossible. We will talk in this course about problems that are literally impossible to solve. With any computer we think you can build in the physical world. But we're merely talking about problems that we think could take you longer than the age of the universe to solve. Okay, so that yes, your computer operating on some idealized laws of physics could solve it, but in fact long before it had done so, the whole the sun would have gone cold, the whole universe would have disintegrated into black holes and radiation, and you would have a problem just finding a power source for your computer. Okay, so this is the sort of thing that we're after, and in order to get that kind of behavior, what helps is to find a problem which is exponentially hard, by which we mean for which the amount of time needed to solve it increases exponentially with the size of the problem. So, here's what linear growth looks like. Here's what quadratic growth looks like. And exponential growth kind of looks like that. It doesn't fit on the board. Okay, so what kind of problem, what kinds of problems are there where, for all we know, they're exponentially hard to solve with today's computers? Okay, well, so one famous example is the factoring problem. Okay, where I give you a number, you're supposed to factor it into primes. Okay, 21, 3 times 7, right? Or I give you some other number. Okay, factor this, right? Okay, here I can, I can at least make it so that one of the factors, right? By just picking the last digit. Okay, but even then, to find all the other factors, right? It could take some time, right? I mean, there's a reason why, they in elementary school they teach you how to multiply, they teach you how to divide, right? But they don't tell you an algorithm for factoring, right? Because the obvious algorithm, could say the trivial one is just try every possible divisor, right? And just see if any of them work. Does anyone know? Can anyone suggest an algorithm that's at least a little bit better than that? Yeah. Yeah, try all the prime divisors. Although one issue is that you got to know which ones are prime. But but there are things you can do there, right? There's like the sieve of Eratosthenes, where you just cross out the ones that are divided by something else, right? There's also, we're going to come back to this point in the course, okay? But if you just want to know if a number is prime or composite, and you don't need to know what the factors are if it is composite, that turns out to be much, much easier than actually factoring the number, okay? And that's a very important point for cryptography and for all kinds of things. So yes, you could do that. You could only test the primes, but all right, but there's still a fairly large number of primes. So yeah. Yes, you only ever have. This is an important. This is a good point. You only ever have to go up to the square root of the number you're trying. Well, why is that? Mm-hmm. Exactly, yeah. Because, if there's a divisor that's larger than the square root, then clearly there's also a divisor that's smaller than the square root. All right, so you're going to find the smaller one first, and then, and then you're happy. All right, once you find the divisor, then you can just divide it, and then you've got a smaller problem. All right, so, okay, so if we think of, let's talk about asymptotics. If we think about n as, say, the number of digits in the number, say the number of decimal digits, could also be the number of binary digits. Yeah, let's take let's actually take n to be the number of bits needed to specify the number. Okay, it's the number of digits when you write it out in binary. That's about 3 times the number of digits when you write the number out in decimal, right? But so then the sort of the stupid trying every possible divisor, that's something like 2 to the n time, right? 2 to the n times the number of time, there are 2 to the n divisors, and then, maybe it takes n squared time, somewhere around there, to try each given divisor. So let's just say, the leading order term is 2 to the n. Okay, if you only go up to the square root, then what's the leading order term? Well, square, yeah. Yeah, exactly. It's the square root of 2 to the n, which is 2 to the n over 2. Okay, still a lot, it's a little bit of a milder exponential. Now, turns out that the fastest known factoring algorithm that we have today is called the number field sieve. It's from the late 1980s, I think. It uses elliptic curves, and its running time is conjectured to be about 2 to the cube root of n. Okay, so so like there's some very, very plausible, and experimentally true number theory conjecture that, assuming that it runs in that amount of time, if you want to rigorously prove in running time, then it's 2 to the square root of n. Okay, but empirically, the running time should be about 2 to the cube root of n. And so what this says in particular is that you can you absolutely can beat the just trying every possible divisor. That's not the best that you can do. Okay, but on the other hand, we would still generally call this exponential growth, right? In particular, if n is in the, first of all, the constant, in the exponent in front of this big O is pretty large. But second of all, if n is in the thousands, right, then 2 to the cube root of n, is still a reasonably large number. And and so this is, for better or worse, this is considered good enough that we, base the security of almost all of our electronic commerce on, the belief that this that the factoring problem is hard. We base it on that, in combination with a whole bunch of other beliefs, like that, the company that that you're trusting just hasn't made some, back deal with the NSA or whatever, right? Which, in practice, I would actually be much more worried about those other beliefs than I would be about the efficiency of factoring. But all right, but so now so supposing that we believe that factoring is hard, meaning that the best algorithm for factoring that there is takes something like this amount of time, which this is not a proven belief. Let's be clear about that. But but supposing that we're willing to make that hypothesis, how could we use this to solve the online gambling problem? So the question is, how can we use factoring to fulfill the role of the safe or the envelope that we wanted before? Yeah.
So you could choose a prime number that, for example, would be 5 if it's red, or whatever.
Yeah. Yep.
Assignment of prime.
Yep.
Then multiply it by some other prime.
Mm-hmm.
And say that the lower one determines itself.
Yeah.
Publish the prime.
Yeah, excellent. Yeah. So yeah, all right. So we should be a little bit careful about the digits, right? The only prime that ends in 5 is 5, right? But okay, but like except for stupid stuff like that, what you said basically, it works. So okay. So we do have to make an assumption, strictly speaking, that's a little bit stronger than just that factoring is hard, right? We need some like binary property of the factors to be hard to determine. So like let's say, let's make a stronger belief, or let's make a stronger hypothesis that it is intractable to determine whether your given composite number has a prime factor that ends in a 3. Okay, now that doesn't follow from the mere belief that factoring is hard, right? You could imagine that there could be an algorithm that just tells you, yes, your number has a prime factor ending in 3. You say, what is that prime factor? And the algorithm says, well, I have no idea, right? I just, like you could imagine that, right? It sounds a little bit silly, but then again, we do have algorithms that are kind of like that. Like they tell you, yes, your number is composite, right? And you say, what are the prime factors? And they say, I have no idea, right? So, you could imagine that, okay? But as far as we know today, there's not an efficient such. As far as we know today, the fastest algorithm, even just to determine whether your number has a prime factor that ends in 3, would be this number field sieve. Okay, so supposing that we're willing to believe that, then what you could do is, let's say you're the user, you're the gambler, so you place your bet by choosing 2 huge prime numbers. Okay, and already here there's a bit of a question of how do you do that? As we said before, there are efficient primality testing algorithms. There are efficient algorithms, something like n-cubed algorithms. That just tell you whether your number is prime or composite. Okay, we've known probabilistic algorithms that do that since the 1970s, and we'll discuss probabilistic algorithms later in the course, and maybe even say a little bit about how these algorithms work. Okay, a deterministic fast algorithm to tell whether a number is prime or composite, that was only discovered in 2002 by 3 people in India, two of whom were undergrads at the time. Okay, and that's the kind of discovery that you remember where you were and what you were doing when you heard about it, at least if you're in this field. Okay, so anyway, we know how to do primality testing efficiently. Okay, okay, but then there's still a remaining question, about how do you pick 2 large random primes? Right? What's the other question that we would have to deal with here? I mean, besides just knowing whether a given number is prime or composite. Well, we'd have to know something about how many primes there are, right? Because if the primes were just really, really, really thinly spread out, then you could just keep guessing 200-digit numbers for an incredibly long time before you happen to find one that was prime, right? So this still wouldn't work for if you wanted to generate a huge random prime number. So fortunately, we know the question of how how are the prime numbers distributed? How spread out are they? This is not a question that's escaped mathematicians' attention, to put it mildly. Much of, you could say a large fraction of all the mathematical effort, in the history of math has gone into questions like this one. So I'm sure that some of you read about the breakthrough that there was just a year or 2 ago when Yitang Zhang, proved that there are infinitely many pairs of prime numbers that are only at most 70 million apart. And that's since been improved to, there are infinitely many pairs of prime numbers that are only 1,000 apart. The ultimate, and this was all over the media. That it's in the New Yorker, this week, I think, because of Zhang's personal story that he couldn't get a job. He was working at Subway, and he was but meanwhile he was working on prime numbers. Okay, so the ultimate goal here is to prove the twin primes conjecture. That would say that there are infinitely many pairs of primes that are 2 apart. Okay, so we don't know that. But one thing that we do know is let me put it this way. Okay, suppose I choose an n-digit number completely at random. Does anyone know roughly what is the chance that it will be prime? Someone else? Yeah? Yeah, it's about 1 over n. Yeah, it's I think it's about so all right. So the number of primes up to capital N, let's say, is asymptotically it's about n over the natural logarithm of n. And from this, you can work out the exactly what's the chance that that an n-digit number is prime. It's c over n for some constant c that I don't remember. So as you go out to larger and larger n's, this becomes a better and better approximation. The question of exactly how good an approximation it is not we don't know the answer to. Does anyone know what that question is called? How good an approximation this is? Well, it's called the Riemann hypothesis. So that's a big question. Okay, but we know that eventually, it does become a better and better approximation. Yeah. Oh, I'm sorry. Capital N, you could think of it as like 2 to the little n. So capital N is like if I ask how many primes are there up to a given number. How many primes are there up to capital N? Then that will be about capital N over natural log capital N, right? Then if I ask what is the chance, that a number that has little n digits is prime, right? And the largest number with little n digits will be, well, depending on whether we're talking about binary or decimal digits, will be 2 to the little n or 10 to the little n, so then that will be capital N. Okay, great. So, yeah, and okay, by the way, this is sort of something you should get used to in this course, that sometimes we have to sort of shift up and down by an exponential. Okay, so all right, so anyway, so what this means is that, like, yes, the primes do thin out as you go to larger and larger numbers, right? That's not very surprising, right? And we've sort of all, like, noticed this in grade school, right? It's like, yeah, as you go out to larger numbers, there are more possible things that that could divide your number, and so there's a smaller chance that your number is prime. Okay, but this thinning out process, what this is saying, and the theorem that does thin out at this rate is called the prime number theorem, right? That should give you some idea of its importance for math. It was proved a little over 100 years ago. Okay, and So what the prime number theorem says is that the rate at which the primes thin out, is not that great, right? So even when you get up to, say, 1,000-digit numbers, there's still roughly 1 in 1,000 of them that are going to be prime, right? Which means that you would merely have to choose about 1,000 such numbers, before you happen to hit a prime. Okay, and in fact, any time that have any of you had to generate a Kerberos ID and it says like waiting, you have to sit there for like 10 seconds while it generates your ID, right? Well, what's it doing? It is trying to find some huge random prime numbers. Okay, it's trying to verify that they're indeed prime. Okay, and then once it finds them, then it can multiply them, and that's a public key. And the prime factors themselves are a private key. Okay, and we'll explain exactly how it works later in the course. Okay, but to come back to online gambling, what you can do is it actually doesn't matter for this purpose which player starts. It could be either one. Okay, but let's say the gambler chooses numbers P and Q chooses two huge random prime numbers, P and Q. Okay, and if at least one of the numbers ends in 3, then this is taken to mean that the gambler is betting on black. And if neither of them ends in 3, then this is taken to mean that the gambler is betting on red. Okay, so, and then the gambler multiplies the numbers. Okay, and multiplying, is something that at least your computer can do very efficiently, right? Certainly like in the number of digits of the numbers squared, something like that. In fact, you can even multiply numbers better than that. Does anyone know what's the fastest multiplication algorithm? I'm sorry. So there are multiplication algorithms that take time, which is like that multiply n-digit numbers in something like in time like n times log n times some really, really, really slowly growing stuff, like the iterated logarithm and these really slowly growing functions. Okay, basically n log n. Okay, these are algorithms based on the fast Fourier transform. But anyway, you use one of these algorithms, multiply the numbers, you send n over to the casino, and now the casino essentially has your bet in a locked safe, right? That's what they effectively have. Okay, so now the casino can go ahead and tell you how what the ball landed on, whether it was black or red. Okay, and then finally we have what's called the decommit stage, which is when you reveal the factors of the number. Okay, so at this point you can say, the gambler can say, here's the factors of the number. The casino can then check to make sure that that those really do multiply to n. Okay, that's important. Otherwise, you could obviously cheat. Okay, and and then they can check that that yes, P and Q do encode the bet that they can then check whether that bet was a winning one or not. Okay, can anyone think of anything else that the casino should also check besides that P times Q equals n? Yeah. Make sure they're both prime. Yeah. What could go wrong if one of them was not prime?
You send a product of 3 numbers.
Yep.
Which ends in 3, one of which ends in 1.
Yep.
And give them either the 9 or the 1, or 3 or 3, depending on what you want your bet to be.
Exactly. Yes. Yes. Okay. Everyone understand that, right? If the numbers were not prime, right, then you could have sent a product of more than 2 primes, and then you could have just factored the number in a way of your choice, depending on what you wanted. Okay, so but as long as P and Q are both prime, there's an important theorem that sort of helps us, that sort of proves the soundness of this protocol. It's not the prime number theorem. It has a different name. Anyone know the other theorem that we want here? Well, we want the fundamental theorem of arithmetic, okay, which says that every positive integer can be factored into primes in exactly one way, up to the ordering of the prime factors. Okay, that's that Euclid proved 2,300 years ago, and that's important for us because otherwise, if your number had multiple factorizations, then you could always just wait for the casino to say whether the ball was black or red, landed black or red, and then just, give the factorization that corresponded to whatever would win. Okay, so it's important that every number has exactly one factorization, and that's but by the way, that's not true over arbitrary number fields, right? There are other number fields, or other rings other than the positive integers where you don't have this property of unique factorization. Okay, but yeah. Oh no, the casino doesn't need to. Okay, so that's a good question. It's important that the casino doesn't need to have a giant list of all prime numbers. Instead, they can use one of these primality testing algorithms that I mentioned before, right? So again, it's very important that that there are fast algorithms, to tell you whether an n-digit number is prime or composite, so they can run those algorithms on P and Q. Mm-hmm. Yeah. And both of these properties of the factoring problem, the fact that factoring, as far as we know, is hard, but also the fact that telling whether your number is prime or composite is easy. Those are both of central importance in modern cryptography, right? Okay. Now, one thing that we're going to do a few lectures on at the very end of the course will be quantum computing. Happens to be what I work on much of the time, and as it turns out, it was discovered 20 years ago by Peter Shor, who's in the applied math department here, that a quantum computer could factor numbers efficiently. Okay, which means that if the casino has a quantum computer in its basement, then this entire scheme is broken. Okay, now there are and we'll explain a little bit about how that works. Now, even a quantum computer would not be able to do absolutely anything. So, yes, it can factor huge numbers. The way that it does that exploits sort of very special properties of the factoring problem. Okay. Ironically, some of the same properties that make factoring as useful as it is for cryptography. Okay, but very special sort of number theoretic properties. We do know of, if you just want to run this online gambling site, then we do know of other cryptographic methods to do that as far as we know, would not be breakable even with a quantum computer. Okay, so, all right, so actually, when I said that everything that you learn in this class is going to be completely useless, I mean, it's like, in the history of math, aiming at uselessness has repeatedly sort of been this, one of the best ways to achieve usefulness, right? And so cryptography is one of the clearest examples of that, right? And it's one of the, cryptography is sort of the place where the sort of theoretical concepts that we're talking about, are the most directly and most obviously have real world implications, right? There are other places, but cryptography is certainly one of the most striking. Okay, so and that's and part of the reason is that with cryptography, it's like you don't have to just theorize about well maybe there's a hard case of your problem. If there's a hard case, well for God's sakes that's what you're using, right? Because you're trying you've got someone who's trying to make the problem hard. And and now you really had better be confident that this problem is hard, and you'd better be confident that no matter how clever anyone is, they're not going to be able to solve it efficiently, okay? Because the entire setup is adversarial, okay? And so and that's what theoretical computer science is all about. It's about how certain can you be, right? About what are the ultimate limits of what someone can or can't compute. Okay, so it's a great field for anyone with like a mathematical cast of mind. It's also a great field for really paranoid people, right? Who are sometimes are the same people, right? But okay, good. So that was just to kind of whet your appetite, okay? But but we're going to circle back to to cryptography, to efficient algorithms, to quantum computing, to sort of all the different things that were sort of illustrated by this little vignette. Okay, but we've got a lot of stuff to sort of build up to before we can really rigorously talk about these things. Okay, like what exactly is an efficient algorithm, right? What's even the right way to formalize what we're talking about, right? And it took people a while to figure that out, and get it right, because it wasn't obvious. And you could say to some degree it's still not obvious, right? Because people came up with a definition of what they meant by efficient computation, and that definition worked extremely well for decades, but then it left out quantum phenomena, right? And the result was that people were led to believe that the factoring problem is hard when when you take quantum phenomena into account. Actually, it's not hard. Okay, so we're still sort of trying to figure all these things out. Okay, but we're going to have to start somewhere, and so roughly like a rough outline of this course will be like for a third of it, maybe we will talk about automata theory and formal languages and computability. Okay, so we'll sort of see the and circuits. Sorry. So we'll sort of and these are just sort of models that will sort of get ourselves used to talking formally about computation. Okay, proving theorems about what you can do in a given model of computation, and also what you can't do. Okay, so I mean, to some extent, you could say anyone who's who's really who's done Euclidean geometry in high school, right, and who got good at like doing ruler and compass constructions, is already familiar in some sense with a model of computation. Okay, you could say that what kinds of geometric figures can you construct using a ruler and a straight edge only, right? This was sort of the first theoretical computer science question, that humans ever asked, if you want to be a little bit anachronistic about it. Okay, so the ancient Greeks were very, very interested in questions like, I'm given 2 points in the plane. Okay, now I'm allowed to, given any 2 points, construct a circle that's, contains 1 point and is centered at the other point. So I could do that. I could do that. I'm allowed to, any place where 2 things I've drawn intersect each other, I'm allowed to, note that as a point. Anytime I've got 2 points, I'm allowed to draw, a line that passes through them. Oh, look, I just bisected this line, right? Whoop-de-doo, right? So, so that, and then once I know how to do something, then I can just sort of encapsulate that thing. I can treat it as a subroutine, right? I can now say any future time that I might want to bisect a line, okay, or construct a line that's at right angles to another line. Okay, now I can just do that because, I know it can be done. Okay, so just like with any other model of computation, you're allowed to use modularity, right? You're allowed to build up subroutines and then call them, and then, but then where things really, and you can do amazing things in this model, right? So Gauss, when he was a teenager, figured out how to construct a regular 17 gun using, ruler and straight edge only. In fact, also a regular 65,537 gun, right? And and so on for certain for primes of the form 2 to the 2 to the n plus 1, I think, right? And, he was so proud of that, even like at the end of his life, when he'd done so many other things, that he asked that a regular 17 gun be inscribed on his tombstone. And apparently you can go there in Germany, and and it's there, but the carver just basically made a circle, because it's like you can't, if you try to carve a regular 17 gun, it really just looks like a circle. Okay, but where things really get interesting is when you start asking, what are the ultimate limitations of this model? What kinds of figures can you not draw, right? And there was this ancient question of squaring the circle, of trisecting the angle, right? And there was this problem of duplicating the cube, right? Which was a strange way to put it, but in modern terms, what it really meant was just you're given a line of length 1, you're a line segment of length 1, and now you would like to construct a line segment of length cube root of 2, right? So if you want to construct a line segment of length square root of 2, that's easy to do. How do you do that, anyone? Yeah. Yeah, exactly. You can make a right triangle, right, which there are various ways to do it. But, here you go, 1, 1. There you go. There's your line segment of length square root of 2. Okay? But now, you want to make a line segment of length cube root of 2. Much less obvious how to do it, right? There's no analog of the Pythagorean theorem involving cube roots, right? Which is itself an interesting fact. Okay, but people just for almost 2,000 years, right? People just figured, all right, fine, we're probably just not clever enough. Okay, and again and again, there would be people who would come up with ways to do it, right? Or they would have proofs that here I can duplicate the cube, right? Here's my construction, and often it would kind of look close, right? It would be they would construct some segment that was whose length was the cube root of 2 up to a few decimal places, right? Which indeed you can do, right? And sometimes, you would have to really squint at it and really study it to sort of figure out where the error was, okay? And a not completely unrelated note, like I get, every week or two, I get an email proving P equals NP, okay? So, and sometimes, you really have to, if you really wanted to pinpoint where the error was, it would take quite a bit of time, right? Okay, if someone claims to prove P is not equal to NP, then then that's kind of can be a hard case. Sometimes you have to find the error. If someone says that they've proved P equals NP, and they say that even the algorithm is efficient, then I just say, so go factor, 2,000, this 2,000-digit number that I'll give you a link to, and then after you've shown me the factors, and I've checked them, then I'll be happy to discuss further, right? And then you sort of never hear back from them after that. Okay, but it took until the mid 1800s for people to really sort of step back and say, well, can we engage in meta reasoning about this ruler and straight edge model of computation? What are the ultimate limits of this model? Okay, and and then they started thinking about it like algebraically, right? About just like what possible lengths of line segments can you construct? Starting, and what they realized was that anything that you can construct, is going to involve just starting from 0 and 1 and then doing some arithmetic operations on them, like adding and multiplying and dividing, and also taking square roots. Okay, why? Well, because basically, if you did geometry in the Cartesian coordinate system, right? So you had an xy plane. You could label every point by its xy coordinates, and then every time you're constructing a circle, you're constructing a line, you're looking for the intersection of them, right? The intersection of like a line with a line is just the solution to some linear equations, right? In two variables and two unknowns, right? The intersection points between a circle and a circle, or between a circle and a line, are the solutions to a quadratic equation, right? And a quadratic equation, so I'm sure you remember from high school, can be solved using square roots, right? So you're always just basically using these operations. And so then, the question can be boiled down to a simpler one of, can you, by starting with 0 and 1 and then iterating these operations some finite number of times, can you produce the cube root of 2? Okay? Certainly you can get closer and closer to the cube root of 2. That's not hard to see. But can you get exactly there after a finite number of arithmetic operations and square roots? Okay, and so that's a very interesting question. The answer turns out to be no. And there's a very, very lovely proof using Galois theory, which I won't show you because it involves Galois theory. But it's actually, if you take an abstract algebra course, it's one of the easiest ones of this form. Like, if you want to prove that you can't square the circle, for that you need to know that pi is a transcendental number, and that's a much harder theorem to prove. This one is comparatively easy. Okay, but we won't do it. But in this course, we will see many other examples of impossibility theorems for models of computation. Okay, where we define a set of rules. Here are the allowed operations, and then we see some examples of things you can do with those operations. But then we step back and we say, here's what you're never going to be able to do, no matter how many times you iterate these operations. And that tends to be the kind of result that we really prize in this field, right? I like the way that Zipser puts it, right? Which is that when you discover an algorithm, you discover how to do something, all you've really done is just found an obstruction to an impossibility proof. Okay, so because the impossibility proofs are the things that really require you to understand all the possible ways that you could do ever hope to do something, and really just understand the entire space of possibilities, right? So and impossibility proofs can be hard to come up with, right? And one of the central reasons they can be hard to come up with is sometimes they're false. Right? Sometimes you actually can do the damn thing, right? And that's kind of annoying when it happens. Okay, but all right. So anyway, so we'll get our feet wet in sort of the first third of the course, talking about models of computation and their limitations. We'll talk about circuits, and then finite automata, which are like computers, but that are only allowed to scan the memory in one direction, just like from left to right. Okay, and the nice thing about finite automata is that we more or less completely understand them. Okay, so there's a whole very, very elegant theory of them that was more or less completely worked out in the 60s and 70s, right? I mean, not that there aren't open questions that you can ask, right? But there's a very, very very, very nice story, and it's very pretty, and and it's useful, again, useful, but it does get used in compilers and programming language semantics, and also in computational biology, things like that. So it's really worth knowing. Okay, and then we'll talk about Turing machines. And the theory of computability, will relate it to Gödel's incompleteness theorem, because those two were sort of born around the same time. And, they're not the, Turing's unsolvability of the halting problem and Gödel's incompleteness theorem are not the same thing, but they're very related to each other. And you can actually use Turing machines to prove Gödel's theorem. We'll see that. Okay, and then we'll start talking about complexity theory. So what changes when you put in a notion of efficiency? You say, Again, you want your algorithms to terminate within the lifetime of the universe. Okay, and then that will lead us to the P versus NP question, which I'll assume some of you have heard of, but it's a very big. If you haven't, it's a very you will have heard of it by the end of the course. It's a very very big question, and we'll talk about NP completeness. Okay, which is one of the the major things that we do know about the P versus NP question. Okay, and we'll see how to take a huge number of problems and say, even though we cannot say for any one of these problems whether it can be solved efficiently or not, we can say that these are all the same problem in some sense. If any one of these can be solved efficiently, then all the rest of them can be as well. And then we will talk about what changes in the theory of computing once we incorporate the notion of randomness. And we'll circle back to cryptography. If we have time, we'll do a little bit of machine learning, which is another application of these ideas. And then we'll do a unit on 4 lectures or so on quantum computing. Okay, so any questions about that? Okay, so I guess all right. All right, I'll just let you out early. All right. And on Thursday, we will talk about circuits. Okay, that will be our first model of computation. Hey, yeah. So, yeah, sure.
I'm taking both this class and 6046. I'm wondering how
Yeah.
much they overlap.
Oh, no, they don't. They're different classes. Oh, yeah. One thing. Well, yeah. The other thing I was going to talk about is 6045 versus 6840 is a question a lot of people have. But so 6840 does overlap with this class. Okay. Yeah, 18404 does overlap with this class. What? Yeah, that's the graduate level version of this class. And compared to 6045, 6840 has, I think, less breadth and more depth. So it doesn't do crypto, it doesn't do quantum computing. It does a smaller set of topics, but those topics it does with greater rigor and in more depth. And it goes into more depth about space complexity, for example. So, if you just want one theory course that will expose you to, as much as possible, then I'd recommend this one. If you want something more mathematically rigorous, I'd recommend that, 18404. If you want, if you really, really love this field, then it wouldn't hurt you to do both. Okay. And also, if you really love this field, then I would strongly recommend doing both this one and 6046 because they have only a very, very small overlap. 6046 is mostly algorithms, is mostly figuring out how to do stuff. And this class is mostly trying to prove what are the ultimate limitations on what you can do. So they're sort of complementary to each other. Okay. Yep. Okay. Yeah.
Does it matter if it's the second or third edition?
It doesn't really. Not that much. I mean, if you have a choice, get the more recent one. But yeah. But it doesn't matter that much. Yeah. Hey. Yep.
I just need you to sign a
Absolutely. Of course.
So right there where the
Uh-huh.
star is, and also this one at the same place.
Okay.
It's one form for each school.
All right.
Thank you so much.
Uh-huh.
Right here.
Yep. Okay, there you go.
Cool, thank you.
Yeah, welcome. Yeah. Hey. Yeah, sure. Of course. Let me take my microphone off.
Is the